Good evening. Have you ever considered how your home is built? As you may well know, homes are built from mycelia, or mushrooms. They are the third kingdom of multicellular life, neither animal nor plant. We use mushrooms to build homes for a variety of reasons: their strength, fire resistance, UV protection, and their ability to be composted and recycled. But it hasn't always been this way. On tonight's special, we'll be taking a deep dive into this technology that revolutionized home construction, from its humble beginnings to its massive implications today. We will also look at the climate crisis, its impacts, and motivation for this mushroom revolution, as well as how we have since overcome these challenges and flourished. Have a look. The story of mycelium in our buildings begins in the year 2022. While there are examples of experiments and prototypes with mycelium prior, 2022 is the year when mycelium first was used to make the insulated concrete form, the direct predecessor to the mushroom-based construction products we see all around us today.
In 2022, the world looked very different. Humanity had spent the better part of the last 2 centuries pumping carbon into the atmosphere, burning wood, coal, oil, and natural gas to sate the energy needs of a growing international industrial economy. As carbon and other pollutants poured into the air, water, and ground, the world began to change. Carbon emissions in the atmosphere produced a greenhouse effect over the whole world, increasing global temperatures and throwing the ecosystem out of balance. Extreme weather events were becoming more common and larger in magnitude. Heat waves, hurricanes, and fires all increased in frequency and destructive power.
These were unprecedented times. As a result, millions were at risk of drought and starvation. Many were displaced, in need of new homes and new ways of life that were resilient. But it looked bleak. Governments and industry that profited from using fossil fuels were resistant to giving up that power and money. But many rose up and wanted to make a change. New technologies were developed in institutions like this: the University of Davis, California, an agricultural institution that harbored many new changes. These disasters were serious. They forced people out of their homes to migrate. They caused wars, food shortages, and famine. This forced many people to reconsider the way of life they had lived for so long. The transportation sector, energy sector, and the construction sector had to rethink burning fossil fuels that made contributors to the greenhouse effect and many of the disasters that followed.
Enter Gabriel Bruce, Carolyn Chiu, and Neyer, 3 multidisciplinary undergraduate students who had come to change the world as they knew it. Under the mentorship of Dr. Christina Cogdell, they founded MycoMasonry and developed the first mycelium-based insulated concrete form prototype.
How did MycoMasonry come about?
It was in 2022. After the pandemic, I was teaching a biodesign course at UC Davis, and it was a fantastic group of 3 students, a bioscientist, an economist, and a design/anthropologist. One of them had worked on thinking about ICF, insulated concrete forms, in a previous class and their life cycle, and knew it needed help. And so when they discovered mycelium as a material that had fantastic properties, they decided to create MycoMasonry.
You see, MycoMasonry recognized a gap in building technologies of their time. Wood frame houses and other prefab and concrete systems required a great amount of labor and expertise. But an alternative was becoming more widely popular in their time: insulated concrete forms. Also known as ICFs, these systems are simply hollow bricks pre-made out of an insulatory material, which when stacked by hand can then be filled with concrete or biocement. They were invented in the 1930s and became more popular because of their ease of use with little training. But in their time, the MycoMasonry team recognized that these ICFs were currently made out of very toxic materials.
The 3 biodesigners asked, what if we substituted styrofoam for mycelium composite? The principle is simple. We still use the same general process today, just on a larger, more efficient scale than what resources MycoMasonry had access to. Most ICF manufacturers today source substrate from local agricultural waste. When disinfected substrate is inoculated with mycelium, the two materials fuse together, forming an organic mass in which mycelium acts as a natural binder. Sometimes supplements are added, such as gypsum to provide trace minerals. Mycelium grows best in dark, warm environments. At a stage of sufficient mycelium growth, the composite is mixed with flour to provide mycelium more nutrients, then packed into frames. Over time, the mycelium consumes the substrate further, strengthening the composite until it reaches a solid form. Finally, the mycelium composite is removed from the frame and baked. While MycoMasonry created their prototype over a span of 4 weeks, today we have improved the timeline with precise recipe R&D and synthetic biology to maximize mycelium growth rate.
This is a rare relic from the UC Davis University archives. It was one of the first molds constructed by MycoMasonry. It may appear rough, constructed from plywood, glue, and tape, and lined with plastic bags, but this was their starting place. It allowed them to experiment with many different substrates, such as oak pellets, wheat bran, rice hulls, straw, as well as several different strains of mushrooms, including reishi, oyster, and wine cap. All of these factors contributed to different attributes, such as density, tensile strength, compression strengths, water, and fire retardancy.
Here you see MycoMasonry's original blueprints from the Museum of Mycelium Modernism. Holes were drilled into the walls of their frame to facilitate oxygen exchange. Their ICF walls were 2 inches thick to optimize mycelium penetration and mechanical strength, and the entire brick was 18 by 9 by 9 inches. The asymmetrical interlocking parts were designed for alternative stacking and alignment of the hollow columns where cement would be poured in. The first Mycelium ICFs were intended for residential and small buildings. We've come a long way since then.
Today, most buildings from residential to commercial to vertical agriculture are constructed by mycelium composites and other biomaterials. Our construction is sustainable, and our cities are resistant to extreme weather. This is a far cry from where MycoMasonry started out, however. They faced many challenges in the production of their first Mycelium ICFs. The first ICF from this frame, for instance, was overtaken by mold. Attaining the facilities and materials to grow mycelium without contamination was incredibly difficult. After this, MycoMasonry faced the challenge of optimizing their ICF to be as water retardant as possible, while still retaining the light and airy density that made it convenient for by-hand construction. The team would also have to start testing their own samples for their key physical metrics without fully relying on the outside research they had used thus far, as well as look into using synthetic biology to tweak their own samples. This would require further funding and collaboration with researchers at UC Davis and beyond.
But it did not take long for things to change. There is a great need for this type of technology, and after a few years of workshopping, arranging a lab, and the steady production of iterative bricks, MycoMasonry contributed their first successful prototypes to the rebuilding of homes following the Ukraine crisis and not long after the construction of homes in and around New Delhi as the Indian city faced the hottest recorded temperatures of that time. They successfully filed for a patent, and their success spread, as did the word of the technology. Since then, MycoMasonry and other companies have expanded the applications of mycelium in architecture, with modular panels and liquid substrate extruded from construction 3D printers.
That's right. Since its coming of age in 2022, mycelium has become a staple of our post-climate world and has allowed us to weather the turbulence as we tackle the sources of our emissions and remove the unnecessary carbon from our atmosphere. It has given us homes that provide exceptional shelter with little cost, economic, and to the environment. It has enabled us to build more, everywhere, and ensure housing as a right to communities across the globe. And mycelium housing has provided the world with another major source of food, a very necessary commodity with the Earth and colony populations reaching nearly 9.5 billion people. With this retrospective, we hope you are inspired by the past and for the future. Certainly, innovation will continue within our modern biosphere. Thank you for joining me on this special program. Good night.